We think we have a pretty good handle on the sun. For over a century, we've been charting its famous 11-year sunspot cycle. But what if I told you we've been focusing on the loud, obvious parts, while a much bigger, quieter mystery has been hiding in plain sight this whole time? Let's dive into what we've been missing.
So for decades, when you talked about the solar cycle, you were really just talking about sunspots. These huge, dark magnetic storms have been our go-to for measuring the sun's activity. They're the loud, unmistakable signs that the sun's magnetic engine is firing on all cylinders. But it turns out, they are just the tip of the iceberg. And that brings us right to the heart of the matter, to the sun's big, quiet mystery. Think about this for a second. Even when the sun is at its absolute peak, at solar maximum, sunspots cover less than 30% of its surface. So what's happening on the other 70%? What are these enormous, quiet regions doing? Do they have their own hidden cycle? For years, scientists were completely baffled. The data was just a mess, and the conclusions were all over the map. Some studies said, hey, the quiet sun's magnetic fields have an opposite relationship to sunspots. Others came back and said, nope, they behave in the exact same way. And plenty of others just couldn't find any clear pattern at all. This wasn't just a small disagreement, you guys. This was a fundamental gap in our knowledge of our own star. So, to solve this mystery, researchers first had to figure out a way to see through all that magnetic static that was confusing everybody. The big breakthrough came from a new tool in the sky. Since 2010, NASA's Solar Dynamics Observatory, or SDO, has been staring at the sun nonstop. Its instrument, the Heliospheric Magnetic Imager, or HMI, snaps a detailed magnetic map every 45 seconds. For the very first time, we had this long, unbroken stream of super high-resolution data covering more than a full solar cycle. But having the data was only half the battle. They needed a really clever way to sift through it. So first, they collected all that data. Second, and this is the genius part, they figured out a way to cut through the magnetic noise. Then they basically drew a line, digitally separating the loud, active regions from the quiet ones. And finally, they let software loose to systematically find and count every single tiny magnetic structure in those quiet areas. And this is just a perfect illustration of that noise reduction technique. Look at the image on the left. That's a single 45-second snapshot. It's grainy, right? Like a photo taken in a dark room. You can see some features, but there's a ton of random static. Now look to the right. By digitally stacking and averaging 7 of those images over a 5-minute span, all that random noise just cancels itself out, and the real, persistent magnetic structures emerge crystal clear. It's just like taking a long-exposure photograph of the night sky. Suddenly, the faint stars become visible. And with this incredibly clear view, they finally figured out what was going on. It turns out the quiet sun wasn't really quiet at all. It was telling a tale of 2 totally different kinds of magnetic fields. The sheer scale of what they found is it's hard to wrap your head around. Using this new method, the team identified and tracked over 86 million individual magnetic structures in the quiet regions of the sun. Just staggering. And here it is, the answer to that decades-old mystery. The quiet sun doesn't have one personality, it has a split personality. First, you've got the antiphase structures. Think of these as the rebels. They're small, there are millions of them, and they do the complete opposite of sunspots. When the sun gets more active, they actually quiet down. Then you have the in-phase structures. These are the conformists. They're bigger, there aren't as many, and they march right in step with the sunspot cycle, getting more active when the sun is at its peak. The reason all those earlier studies were so confused is that they were seeing both of these signals mashed together. But as you can see here, if you're just counting the structures, it's not even a contest. At any given time, more than 95% of the features in the quiet sun are those small, rebellious antiphase ones. But here is the major twist. It's not about how many there are, it's about how powerful they are. Those millions of tiny antiphase structures are like a huge crowd of people whispering. But the few in-phase structures, they're like a handful of people shouting through megaphones. And when we talk power, we mean total magnetic flux, which is just a way to measure the total magnetic field energy. And during solar maximum, that shouting from the in-phase structures completely drowns out all the whispering from the millions of antiphase ones. So what does all of this mean for the deep-down physics of how the sun actually works? Well, it means we can finally start to crack the code of the solar dynamo. To put it simply, the solar dynamo theory is our best guess for how the sun creates its magnetic field. Scientists have long suspected there are two engines running, a big global one deep inside the sun that drives sunspots, and a smaller local one near the surface that creates all those smaller magnetic fields. And this new research shows us exactly how those two engines play together. Okay, so here's the key. At the sun's peak activity, at solar maximum, about 60% of the magnetic energy in these quiet regions is actually just the leftover junk from old decayed sunspots. It's like that big global dynamo is running so powerfully that it's just flinging embers all over the sun's surface. Now, watch what happens when we shift to solar minimum. The whole picture flips. The contribution from that big global dynamo plummets to just 10%. The other 90% of the magnetic energy is being generated right there on the surface by that local dynamo. It's this beautiful confirmation of the theory. As the big global engine sputters out, the small local engine really kicks into high gear. So what's the big takeaway from all of this? Well, it's pretty simple. These findings are forcing us to completely rewrite our definition of the solar cycle. This right here is probably the most mind-blowing result of the whole study. For 150 years, we have defined the sun's activity by looking at the magnetic field in sunspots. But this research shows that for most of the solar cycle, the total magnetic energy locked away in the so-called quiet regions is actually greater than the energy in the active regions. We've basically been judging the power of the ocean by only looking at the crashing waves while completely ignoring the massive, powerful currents moving just beneath the surface. And this quote from the researchers who did the work just says it all perfectly. You can't understand the solar cycle by just looking at sunspots anymore. You absolutely have to look at the whole picture, the active regions and the quiet regions, to get a real handle on what our star is doing. And that leaves us with a pretty fascinating thought to end on. We thought we knew our own star, but we were missing the majority of its magnetic story, just hiding there in the quiet zones. It really makes you wonder, doesn't it? What other huge, fundamental assumptions about our universe are based on us only looking at the loudest, flashiest signals, while the real story is waiting patiently in the quiet?